In this initial video, I want to show how you might stumble into the core ideas of calculus by thinking very deeply about one specific bit of geometry, the area of a circle. Maybe you know that this is pi times its radius squared, but why? Is there a nice way to think about where this formula comes from? Well, contemplating this problem and leaving yourself open to exploring the interesting thoughts that come about can actually lead you to a glimpse of three big ideas in calculus: integrals, derivatives, and the fact that they're opposites. But the story starts more simply. Just you and a circle, let's say with radius 3. You're trying to figure out its area, and after going through a lot of paper trying different ways to chop up and rearrange the pieces of that area, many of which might lead to their own interesting observations, maybe you try out the idea of slicing up the circle into many concentric rings. This should seem promising because it respects the symmetry of the circle, and math has a tendency to reward you when you respect its symmetries. Let's take one of those rings, which has some inner radius r that's between 0 and 3. If we can find a nice expression for the area of each ring like this one, and if we have a nice way to add them all up, it might lead us to an understanding of the full circle's area. Maybe you start by imagining straightening out this ring. And you could try thinking through exactly what this new shape is and what its area should be, but for simplicity, let's just approximate it as a rectangle. The width of that rectangle is the circumference of the original ring, which is 2 pi times r, right? I mean, that's essentially the definition of pi. And its thickness? Well, that depends on how finely you chopped up the circle in the first place, which was kind of arbitrary. In the spirit of using what will come to be standard calculus notation, let's call that thickness dr, for a tiny difference in the radius from one ring to the next. Maybe you think of it as something like 0.1. So, approximating this unwrapped ring as a thin rectangle, its area is 2 pi times r, the radius, times dr, the little thickness. And even though that's not perfect, for smaller and smaller choices of dr, this is actually going to be a better and better approximation for that area, since the top and the bottom sides of this shape are going to get closer and closer to being exactly the same length. So let's just move forward with this approximation, keeping in the back of our minds that it's slightly wrong, but it's going to become more accurate for smaller and smaller choices of dr. That is, if we slice up the circle into thinner and thinner rings. So just to sum up where we are, you've broken up the area of the circle into all of these rings, and you're approximating the area of each one of those as 2 pi times its radius times dr, where the specific value for that inner radius ranges from 0 for the smallest ring up to just under 3 for the biggest ring, spaced out by whatever the thickness is that you choose for dr, something like 0.1. And notice that the spacing between the values here corresponds to the thickness dr of each ring, the difference in radius from one ring to the next. In fact, a nice way to think about the rectangles approximating each ring's area is to fit them all upright side by side along this axis. Each one has a thickness dr, which is why they fit so snugly right there together, and the height of any one of these rectangles sitting above some specific value of r, like 0.6, is exactly 2 pi times that value. That's the circumference of the corresponding ring that this rectangle approximates. Pictured like this, 2 pi r can actually get kind of tall for the screen. I mean, 2 times pi times 3 is around 19, so let's just throw up a y-axis that's scaled a little differently so that we can actually fit all of these rectangles on the screen. A nice way to think about this setup is to draw the graph of 2 pi r, which is a straight line that has a slope 2 pi. Each of these rectangles extends up to the point where it just barely touches that graph. Again, we're being approximate here. Each of these rectangles only approximates the area of the corresponding ring from the circle. But remember, that approximation, 2 pi r times dr, gets less and less wrong as the size of dr gets smaller and smaller. And this has a very beautiful meaning when we're looking at the sum of the areas of all those rectangles. For smaller and smaller choices of dr, you might at first think that that turns the problem into a monstrously large sum. I mean, there's many, many rectangles to consider, and the decimal precision of each one of their areas is going to be an absolute nightmare. But notice, all of their areas in aggregate just looks like the area under a graph. And that portion under the graph is just a triangle with a base of 3 and a height that's 2 pi times 3. So its area, 1/2 base times height, works out to be exactly pi times 3 squared. Or if the radius of our original circle was some other value, capital R, that area comes out to be pi times r squared. And that's the formula for the area of a circle. It doesn't matter who you are or what you typically think of math, that right there is a beautiful argument. But if you want to think like a mathematician here, you don't just care about finding the answer. You care about developing general problem-solving tools and techniques. So take a moment to meditate on what exactly just happened and why it worked. Because the way that we transitioned from something approximate to something precise is actually pretty subtle, and it cuts deep to what calculus is all about. You had this problem that could be approximated with the sum of many small numbers, each of which looked like 2 pi r times dr for values of r ranging between 0 and 3. Remember, the small number dr here represents our choice for the thickness of each ring, for example 0.1. And there are two important things to note here. First of all, not only is dr a factor in the quantities we're adding up, 2 pi r times dr, it also gives the spacing between the different values of r. And secondly, the smaller our choice for dr, the better the approximation. Adding all of those numbers could be seen in a different, pretty clever way as adding the areas of many thin rectangles sitting underneath a graph, the graph of the function 2 pi r in this case. Then, and this is key, by considering smaller and smaller choices for dr, corresponding to better and better approximations of the original problem, the sum, thought of as the aggregate area of those rectangles, approaches the area under the graph. And because of that, you can conclude that the answer to the original question, in full, unapproximated precision, is exactly the same as the area underneath this graph.
So I'm going to do integration by parts now, and then I'm going to get on to definite integration. And definite integration is when it starts becoming useful to engineers. So we better get started, haven't we? From differentiation, we know that d by dx of uv is equal to u dv dx plus v du dx. Now, if we integrate both sides, we get the integral of d by dx of uv, and that's equal to the integral of u dv dx plus the integral of v du dx. Now, we already know that differentiation and integration are inverse operations, which means that these two basically cancel each other out. So we can write uv is equal to the integral of u dv dx plus the integral of v du dx. So if we take the v du dx term onto the other side, we can write that the integral of u dv dx is equal to uv minus the integral of v du dx. And this is called integration by parts. Let's do an example. So if we say our integrand is equal to the integral of x sine x dx, we're going to let x equal u and sine x equal dv dx. So let x equal u and sine x equals dv dx. We're going to differentiate u, so we're going to get du dx is equal to 1, and we're going to integrate dv dx, so we're going to get v is equal to minus cos x. Now, as always, if you've done an integration, do a differentiation just as a sanity check. So dv dx, if you differentiate cos, you get minus sine. So if you differentiate minus cos, you get sine. So that's going to be minus sine x, which is obviously the sine x that we've got there. So v is equal to minus cos x. So now we can say that I is equal to uv, which is minus x cos x. So that's uv, and then that's going to be minus the integral of v du dx, which is going to be the integral of minus cos x dx. So now we can say that that is equal to minus x cos x, and we've got a minus here and a minus here, so we can say plus, and then if you integrate cos x, you're going to get sin x plus a constant. As usual, we'll do a sanity check by differentiating this. So we're going to say di by dx is equal to differentiate this part, this is a product, so we're going to use the product rule. So we're going to get u, which is going to be minus x, times, then we're going to differentiate cosine, so we're going to get minus sin x, and then we've got so that's u dv dx, so now we need v du dx, so that means we need cosine times the differential of minus 1, which is obviously going to be minus 1, so that's times minus 1. Then we differentiate sine, so we're going to get cos x, and the constant will disappear. So let's just see what we've got left. We've got minus x times minus sine x, so that's going to be x sine x. We've got cos x times minus 1, so that's minus cos x, and we've got cos x. So obviously the two coses cancel out, which means that we're left with x sine x, which is what we started with. And that's how you use integration by parts. So far we've been adding a constant to the end of all our answers because there is a constant of integration and we don't know what it is. Other times we will take something like, I don't know, let's take a sine wave, which looks something like that. This is 2 pi, this is pi, and this is pi over 2. And we may want to integrate it from one point to another point. And as the video that we've just watched was discussing, this is actually the same as calculating the area under the curve here. Okay, and that's one way of looking at what integration is doing. So what we would do here is we'd say the integral, let's say from 0 to pi over 2, let's make it a bit easy on ourselves, of, we've got sine there, so it's sine x dx. Okay, now that's something that we can integrate quite easily. We know how to integrate sine. That's going to give us, so I is equal to that, and that's going to be equal to, it's going to be minus cos x, and how you write it is 0 to pi over 2. Okay, that's the way you write these things down. And let's just review what's going on here. If you differentiate cos, you get minus sine. So if you differentiate minus cos, you get plus sine. So what we do is we put the upper value into whatever this expression is and get a value for that, and then we put the lower value into the expression and we get a value for that, and we subtract the lower value from the upper value. So what we're going to do is we're going to put in the first value. Now let me just remind you what the cos looks like. A cosine looks like that. That's 2 pi, that's pi, this is pi over 2, and obviously this is 0 here. So if we put pi over 2 in here, we're going to get the first value, which is minus 0, whatever that might mean, and then we subtract from that minus the value when we put 0 in. So I'll stick that in brackets. So it's minus cos x. When x is 0, cos is 1, so it's going to be minus 1. Okay, let me just say that again. So we've put pi over 2 in place of x there. So the cos of pi over 2 is 0, so that's the value there. So that's where that 0 came from. And then we subtract from that, which is why I've got a minus here, the value when we put 0 in there. So the cos of 0 is 1, and we've got a minus there, so that it's minus 1. So that means that our total value is equal to 1. 0 disappears, we've got minus times minus, and the area is 1. So if this was in meters, that would be a square meter. If it was in millimeters, it would be square millimeter. Whatever your units are, that is a measure of whatever it is you're looking at. If this was energy, for instance, if this was a radio wave, that could be in watts. I mean, if this was the energy that's being broadcast from an antennae, you know, for a radio or something, that this would be in watts. So the actual units depend on what your graph is, but obviously it must have some kind of units. Okay, so that is definite integration. Let's do another example. Let's do a polynomial. So we're going to do the integration, the integral, let's say between, let's have some proper values. Let's say between 1 and 3 of 3x squared minus 2x plus 1 dx. Okay, so we're going to integrate this. It's a polynomial, so we can do it term by term. So integrating this, we've got 3x, and then we increase the power by 1, so squared becomes cubed, and then we divide by the new power. Then we get minus 2. We've got x, we increase the power by 1, so that becomes squared, then we divide by the new power. And we take the next term, which is like x to the 0, so we increase it by 1, so we get x, and we divide by 1, so that gives us nothing. And that's the integral. But instead of writing plus a constant, we now put the lower and the upper, the lower and the upper values. So I tend to put a square bracket on there. Some people put a curved bracket on it, but that's my expression. And now what I'm going to do is I'm going to put the value 3 into all of this, and then the value 1. Actually, before I do that, I'll just simplify this, because that's going to be x cubed minus x squared plus x, isn't it? Let's just make it a bit easy on ourselves. So now I'll put the values in. So first of all, I'll put the upper value in. So x cubed is 27 minus 9 plus 3. Okay, so that's the upper value, and then minus the lower value. So 1 cubed is obviously 1, minus 1, 1 squared is 1, plus 1. Okay, so 27 minus 9 is 18 plus 3 is 21. Or to put it another way, minus 9 plus 3 is minus 6, 27 minus 6 is 21, and then we've got 1 minus 1, so they cancel, and we've got a 1 there and a minus 1 there, so that's going to equal 20. Okay, so I is equal to 20. Okay, and we don't need a constant. Okay, so that's definite integrals, and I'd better just do one more. So remember we were saying that the integration is the area under a curve. So what I'd like to do, I'd just remind you what a cosine wave looks like, and I'd like to integrate from 0 to 2 pi cos x. Okay, and see what happens. So what I'm going to do is I'm going to do the integral. So the integral of cos is sine, so that's going to be sine x from 0 to 2 pi. Okay, and if I differentiate sine, I get cosine, so that's okay. And I'll just remind you what a sine wave looks like. It goes like this. Okay, that's 2 pi, that's 0 obviously, and that there is pi. So if I put 2 pi into that, I'm going to get 0, and if I put 0 into that, I'm going to get 0. So according to this, I is equal to 0. Now what we're saying is it's the area under the curve, and yet I somehow seem to have proved that this curve here, because we were integrating the cosine, remember, I've seemed to have proved that the area here, I guess I'd better put a line there, is equal to 0. So what's going on? The answer is the bit under the curve here is less than 0, and the bit above the curve is greater than 0. So this area and this area added together are the same as this area under the curve. So we've got a little bit of a problem here, because clearly if I'm interested in the area under the curve, it's not 0. So what am I going to do in a case like this? The answer is I'm going to say, well, this bit here, let me have a different colour, let's do red. This piece there is equal to that, which is also equal to that, which is also equal to that. These pieces are all identical apart from their orientation. So if I get something like the integral from 0 to 2 pi of cos x, what I'm actually going to do is I'm going to say I'll have 4 times the integral from 0, that's 2 pi, that's pi, so that's pi over 2, so it's going to be pi over 2 of cos x dx. And I should have had a dx there, shouldn't I? Okay, so what I've said is let's just take a quarter of this and then have 4 times that to get the actual value. So now what's going to happen is that's going to equal 4 times sine x from 0 to pi over 2, and that's going to equal, well, here's my sine of pi over 2, which is 1. Here's my sine of 0, which is 0, so it's 1 minus 0, and that's inside a bracket times 4. So the answer is 4. Okay, so be a little bit careful with sines and cosines. Just think what you're being asked. What I mean by that is look at the upper and lower limits and decide whether it's actually crossing the axis or not. If it's crossing the x-axis, then you need to split up the problem into something a little bit smaller. Okay, right, and where are we? We're at 39 anyway, so I think I'd like to go into breakouts now. Okay, so I'm going to stop sharing the screen, I'm going to stop the recording,